Так, тут чуть изменился формат. Я сейчас найду нужный файл. Прошу прощения за небольшую задержку. Rafael, are you with me?
Yes.
Did you obtain my message?
About the first part, the first implication.
Yes. So let us start with your solution, and then we'll discuss the first implication. So can you now try to explain your solution? If you don't want to explain the first implication, I can try to help you. So can you start to explain, please?
So explain which part? The first one as well?
No, the exercise 2, the part that do you see in the screen your file?
Yes, I. So if we take A, which is a convex linear cell,
Yes.
by the course we can write it with equation.
Right.
With a family of Fi, which is equal to 0, and a family of Gj, which is bigger or equal than 0. It's from the course. Then we can just take a subset B in A, and we can just take the smallest face where B is included in.
Right. You denote the smallest face by B bar, right?
B bar, exactly. Can you put big again the window? Yes, and so what do we have? So B is included into A. So by the course we have that B will just be some, so it will be the same family of equations, but we will have that one of the Jg will be equal to 0.
Right.
So we vote. I don't see the window is not. We cannot see fully the text.
Do you see the screen?
I do see the screen, but it's missing on the right side.
Right side.
Yes.
You don't see the right side?
Yeah, what I can, if I read what I see, let's suppose A is a convex linear cell with equation Fi equals 0 and then I cannot see after. Yes, a bit more. Okay.
You see?
Okay, so yes, a bit more, and it will be perfect. Yes, so yes, we define the same Fi, and then we take from G1 to Gk is equal to 0.
Right.
We can do it because B is inside. Okay, and we have some Gk plus 1 until Gn, which are equal or bigger than 0. Now, we can find a point X such that for J, Gj is bigger than 0. If we take, we can take kind of, not exactly a barycentric point, but this is the idea. A point which is not a point which is not on faces. It will give us not 0.
The essential that the point should be in the interior. It not should be in some face, but just in the interior.
Interior. It's just in the interior. Yes. So now the goal is to show that this point belongs to B, and not just B bar, and then it's true for X. So we will have the implication that the face is just equal to B. So now we take a point Y, which is in the face B bar, and we can form a segment out of this point X and Y.
It's essential that you should stress that it is an arbitrary point of B bar.
Yeah.
Right?
We just take some Y in, but it has to be. I mean, this point is arbitrary, but in B bar. So we can form a segment out of it, and then we have a line out of it, and there is a point Z which belongs to the intersection of the line and B bar, and we have that X is between Y and Z, with Z the new point that we just add it right now. Yes. So now we just need to use points 1 and 2. So by 2 we have that given that X belongs to P, Y and Z, or Y or Z, one of them, at least one of them, is not in B.
Right.
But because of the point 1 with the hyperplane situation and the intersection is equal to the substance, so we have that both points belong. So we have that Y and Z belongs to B, and X being in the segment, X belongs to B as well. And then we have that B equals B bar, and we are done.
Right. So did you think a little bit on the
I have a bit of time. I'm not sure how good it is. So again, yes. So we have that B is a face, and we want to show the 2 points 1 and 2. So here again, B can be a system of equation, and we have also that B is included into A, right?
Yes.
So we want to show that the hyperplane, which is spanned by B, the intersection with the convex cell is just B, but if we span something by B, all which will be out of B will be out of A as well. It will be out of the convex cell, convex linear cell. So we have the first point, because
Yes.
What will be what? Yes. Okay. And now, if we take okay, so if we take a point which is in the
maybe
span,
you can. Sorry, I just want to find. Bon, yes, this is the next slide, but I would like to that you make a picture. Would you like to?
how can I make a picture?
Excuse me, I just try to find a proper place somewhere. No. Okay, this is the first lecture, so maybe you can write to make a picture here in the screen. Can you do it?
I don't know how to make the picture from. Okay, how can I make the picture?
No, I don't know either.
Wait, give me 1 second.
Maybe you can write down.
Maybe I can share my screen and I will make the picture on my screen, and then we come back to your screen.
Yeah. Okay. Very good. I
just
try to.
1 second. Just 1 second. Do you see a white blackboard?
No.
I'm trying to. Yeah, I'm asking you to make the.
And now it should work, no?
Yeah.
Okay, so if let's suppose we take just for a picture. So we take the tetrahedron, and let's suppose this is the face we are talking about. This is B here. So of course, if we take the span of this face, and we say that the convex cell is all this tetrahedron, of course the span of this will intersect with A only here. So now let's suppose we take 2 points of the span. So if we take can you read me the second condition again?
The second condition is that no point of P lies between any 2 points in the complementary of B in A.
Okay, so if let's suppose we take a point in P, in the span of it, if we take a point here, well, I mean, from the picture it's obvious. If we take any point of P, it cannot belong because we take out the base of the span, so it will take out all this part here.
So it's in some sense it is the same as the second. you try to find a point in interior, right?
Yeah. But we by the data it's not possible because we take out the face from it.
Right. Okay. So other questions for the proof? Maybe I'll try to actually I wrote down some comments, but I couldn't find it. So sorry, I couldn't find it in the screen. Anyway, so let us discuss the third in your homework. Let us discuss the third exercise, that if you have K is any complex and there is L subdivision, what means that K bar is equal to K, the union of cells, that every cell of K in some sense is union. So every cell of L is the union of cells of K. So this means that formally it doesn't mean that this is true for the general definition of subdivision. The subdivision is this, and it is necessary to prove this. So you are taking any point, and please continue.
Yes. So first, because of the subdivision, we have an equal number of cells. So we just need by taking any cell A in L and a cell B in K,
right?
And A in B. We just need to show that B is in A, and I think I should say that little a also belongs to big A. Yes, I forgot to write it. Because we can just write A as a union, and we will have a union of subcells.
Right.
K. So first we fix. So we take any cell A of L. Yes, of L, and by 2 we already have that for a cell A prime in L we have a cell B prime which is included in A prime, and we can say that A belongs to B prime. Now we are just using the definition. We have that A intersection of A prime is just the common face of A and A prime. So this face we call it A double prime. Furthermore, we have that B prime is included in A prime. That means that we will have also an intersection between B prime and A second prime, and it's also a face by definition. We can call this face, so the intersection of B prime and A double prime, B, and this gives us the result that we want.
Okay, but as for me, I don't see that we need this cell A two primes. As for me, A intersection with A prime is already B. Why you need this A two primes? is gone.
A2 prime is a face that A and A prime have in common. And
Right.
then we even make it smaller with the B prime. That's all we are doing. We have a face which is common of A and A prime, and we take a subcell of A prime. So the intersection of this subcell with the face will give even a smaller face. And this smaller face will give us what we are looking for.
But look, as for me, you see B prime is in A prime, right?
Yes.
And it is also okay with A, right?
Yes.
And so what is the problem? You can just call this as B, and it will be the cell what you need.
Yes. So there is one step which is not useful. Yes.
So as for me, it's just okay, because even formally you have that it is how to say that two cells is okay. So you, for example, the crucial fact is that you prove that B prime is in A prime, right?
Yes, this is just by using 2,
okay.
Condition 2.
Yeah, and this is also true for A, right?
Yes.
And both of them are the cells of L, right?
Yes.
So intersection of them is a cell of L by the definition of the simplicial complex. So if I baptize this cell as B, I have already this inclusion. You really write this. B prime is in A prime, but B prime is also in A. So this is just okay.
Yes.
Just okay.
This.
Of course, it's not the mistake that you have done, but it's in some sense this is tautology, because B prime is an A n prime, so B prime is A prime too. So they are so this this is definitely okay, right? But anyway, okay. So very good. We've finished with these exercises, the previous exercises. So did you look at the exercises which I sent today in the morning?
I took a look, but I didn't have time to solve it right
okay,
away.
So next time.
One I started to think about it, but with the Reidemeister moves, it's a bit more tricky, no? From what I understand.
Yes, that's why I made this. But at first, can you show this by moves, by the isotopy? Can you show by isotopy? How can you see just have a small game for for children how to make this knot trivial.
So we have on the extreme right, we have this part of the rope which is actually under everything. So we can.
No. Extreme right. It is no. Look here.
Yeah.
I can show a picture if I can.
Raphael, we shall. Yeah, we shall see what Natalia will show us. Okay.
Okay, sure.
Okay. I cannot show my picture because I cannot share. You must stop your demonstration.
I don't know how to do this. Can you help me? This is the first time I'm using this because in the department in the High School of Economics they gave me this new stuff, so I first time I'm using it. You see,
it's problem.
Yeah,
I cannot show my picture.
but
if you can stop, cannot stop, I cannot show.
How can I stop? Can you tell me?
Maybe
Stop demonstration. I stopped.
Okay, thank you.
Yeah.
Okay.
Okay. Very good.
The first picture. Okay.
Right.
Так, тут что-то у меня тоже не получается.
No problem. We have enough time. The first time your picture was okay.
Okay. The first picture.
Can you do the same thing that to see your screen, to see the image of the picture that was before?
Can you see my picture? But you can see only one picture, and I cannot second picture.
You have several. So what can I do?
Sorry, this is my first time.
No problem. All of us are doing the same thing. You can try in your picture, you can try. Yeah, we see it.
Okay.
You can explain.
Can you see my picture?
Yes.
This first picture, this is the second picture.
Right.
Can you?
Right.
Okay.
Right.
And,
right. Very good.
Very this good. Is my picture. Okay.
Yes. Yes.
And this. And this.
No. Can you? The second I understood. You just pushed to the right, but the next one, what are you doing? You are putting.
Okay.
You are putting here, right?
I don't hear. Repeat, please. This is
So
first, second, and
first thing you put this,
okay,
which is below everything. You put here to the right hand side.
Okay.
Very good. Then what are you doing then?
Okay. next picture and next picture. And
yeah,
next
sorry, it's too quick for me.
Okay.
The second, please, the second one.
Second.
The second, your second picture, right? So now stop, please. Okay, so now explain.
Okay.
And then I would like to say what I will do. And you say in words, not touch the picture, please. Say in words, what are you doing?
I take...
your picture. No, your picture.
Okay.
Which was the
Okay.
Whoa, stop
This?
here. Yeah, not move, just
Okay.
explain what are you doing.
I take down line and move right and up.
But I would like to say what I do in this case. Do you see how I'm moving? You see
No,
my arrow? Raphael, do you see my arrow, how my arrow is moving?
No, we just see the picture. We don't see anything else.
You don't see okay, so okay, I'm afraid if I take demonstration of screen, then I may be returned to my own. So I explain. You see the picture, Raphael?
Yes, I do.
So there is a line in blue in the right-hand side.
Yeah, it's the line that was.
And then is the second, which is almost parallel.
Old line is.
Then I would like to move, because now this is what Raphael was saying at the very beginning, that but not only now it is true that this piece of line, starting from here, it is below. So I would like to put it to the left-hand side, like there.
Not on the right, on the left.
Yeah. Now I would like to put it on the left-hand side. I made a photo of my pictures, and if I couldn't.
Oh, in my pictures, the right-hand side. No.
Yes, but this is exactly maybe the same. So I saw in your picture that now you are trying to shrink your blue line to a smaller part, right? You're trying to shrink. Now look, your blue part is going around everything, and you are shrinking it to a small scale, right? This is what I'm doing.
Right? Maybe. In this picture, old line we see as white, and I move white line, and we can blue line.
Yes, but I'm speaking about the next step. The next step.
Next step.
Oh yes, you are shrinking, so it is visible that you are shrinking the blue line. It was a big one, and now you are deforming it to a small piece, and finally you put it in between these two lines, right? Okay.
Right. Yes.
Slowly. The next picture, please.
Next picture.
Oh yes, that's what I'm saying. You are shrinking your blue line. So you are doing a little bit different things, but you are shrinking now. Okay, very good. And now you see that your blue line is under the next line, and you are continuing to shrink, right?
Yes.
Yes, you are shrinking it and made it over there. Now you see that this piece is going over everything, right?
Yes.
Yes. So, and now it's done. So, for example, here, look, if you see this one, but we'll discuss in detail about Reitermeister.
This is two Rademaster.
Yeah,
and we have this.
Yes, okay. and finally, formally, you see that this is the first Rademaster to kill this or this.
Yes, first Rademaster, and we have
yes.
trivial circle.
Okay, very good. Raphaël?
Yes, I understood.
Vous êtes convaincu?
Je suis convaincu.
Très bien, très bien. Voilà. But as for me, I was not shrinking the blue line, but I moved this one. After that, I moved this on the right and on the left, sorry, and then it was more or less. So it's depend on your psychological properties how to do. Very good. Now, other questions? Anybody else? So the number 79139. Do you have any problems? Are you with me? Okay. If no problems, we'll start. And then again, now, as you've seen, this is a bit more tricky to use formally Rademaster. I have in this screen, but I'm afraid what where is my Rademaster? Sorry, Rademaster. It was maybe the lecture 3. Oh, this is terrible. No, this is exercises. No, I'm sorry. Where is the? No, this is a new one. What's this? This is again our exercises. Sorry. And this is no, this is lecture 1. We don't need it. Again, lecture 1. No. What is it? Lecture 3. So sorry, this is my terrible stuff. Just want to remind you, Rademaster. So there is Rademaster 1, Rademaster 2. You are moving. We see the last in the last stage of our moves that we are using this. And of course, the most complicated is the Rademaster 3. Okay, I remind this Rademaster, and then sorry, we return. So, Raphael, do you have ideas?
Well, my question is, for example, we have a knot on the top, right? But even if we want to use Rademaster move, we have a problem because behind it, we have a problem to use it here.
Yes. Yes. But to use Rademaster moves, you should also have in mind that you can freely make isotopy of your picture if you don't change the type of the diagram. If you don't, you have, for example, I propose the following thing. We shall do this by Rademaster move, but I propose to do the same thing as Natalia was doing, to make the move of this line. Do you see?
I can, sorry, I can see my moving as step by step for the master.
Very good. That's what but only thing, you need to be very, very patient to do this. For example, your move, Natalia, will be the following. I'll try to.
I can see picture, but
yes.
If you can stop your demonstration.
Yeah, but I just want you to say only one thing, that we first of all we make the following thing. Do you see what I'm doing?
Yes.
Natalia?
Yes, yes.
So this is completely possible because you are Reidemeister moves. What they are need? They are need when you are changing the structure of the diagram as a graph. But if you only making isotopy and you didn't change it as a graph, it is possible. The isotopy of diagram is okay, no problem. And then, for example, your first Reidemeister move will be the following. Here, at this point, my previous one, I'm not very good in colors, but so
it's so it's become, we have a straight line and we have
the first one, right?
Yeah.
And then you have here the next one, and this will be, now you are also not changing anything. You are also not changing anything, but look now around this point. Natalia, Rafael.
We will have a 3
yes.
3 intersection, no?
No. Oh, yes, finally. So you need to use Reidemeister 3. And this line, you will make this one. So you are changing. So this is the hardest Reidemeister moves. You are now moved here. But there is one subtle thing that you will see later. So now I can stop, and I give a word to Natalia.
Okay, thank you. Yes.
So I only done 2 Reidemeisters. One is when one line goes, and the third one. Okay.
Sorry.
No problem. We are all
okay.
in the same position. I also asking to apologize me when I'm not so clever with these things.
Okay, this is our first knot.
Yes.
And this is our second Reidemeister.
Yes,
okay?
but in our order, this is our first Reidemeister move, right?
Okay, and
very
this
good.
Is our third
Reidemeister.
Okay.
Very good. Very good.
And this is a third Reidemeister next cross. This and this. And
right. Yes.
We have second Reidemeister move a blue line.
Right. Okay. But and actually, I think, yeah, if you want, you can do. Okay, right.
Okay.
Yes.
Can you go back and
Sorry, Rafael, Natalia, let us listen to Rafael.
Okay.
Just one before and this one.
This?
Yeah. Okay, and next?
And we move this line, and we have
okay.
This.
Okay. Mm-hmm.
This is the second Reidemeister move, Rafael.
Yes. Second Reidemeister.
Yes.
Yes. And this third Reidemeister in this intersection. Okay.
Yeah, but
Previous,
probably better to move this around, this blue maybe to make, as you were doing it at first, to make blue around. No?
Repeat, please. We have a third order Meister in this in this intersection.
Very good. Very good. Let it be.
And we have this, and
Right.
first order Meister in this loop,
Right.
and in this loop.
Yes, this is very good,
Okay.
because when I'm making this this picture early for students, sometimes they forget this. They jump from the previous picture, just they smoothing this, and they forget that this is also, usually forget that this is also right mastimo. So Natalia, very good. You are very strict.
And Soster the Meister, and we have this. Our loop is empty, and okay.
Yes.
We have a third order Meister in.
No. Only the second.
No, I have a third order Meister in this cross, and we have this.
No.
No. No.
No.
So sorry.
No.
Sorry.
No. This is just look at this very long.
Yes.
This will be the second.
Yes, you're right. Second order Meister, and we have this.
Yeah, and so we obtained what you were doing by moves, right? Now we obtained formally. Very good. Very good.
Blue line move to right, and we have this. And
sorry, just a moment. I'm asking Rafael, do you with us?
Yeah. I follow.
Very good.
This and this. Okay.
Yes.
And we have a second order Meister, and we have this.
Yeah.
Not cross. It's.
Yeah, this is the damage of the drawing.
Okay. Yes, and we have a second order Meister, and we have this, and we have second order Meister, and we have this, and we have second order Meister, and we have. And this is the same. We have this, and we have second order Meister, and we have this, and second order Meister, and we have this, and second order Meister, and we have this, and first order Meister, and we have a trivial loop.
Yeah. Yes, we can.
Thank you for your attention.
Yeah, thank you for doing this. So you see how it works, okay? So you see how it works. So this is actually the game for children, right? In some sense, this part of mathematics is sometimes simpler to explain for children. You don't need any integrals, topological vector spaces, or even determinants and so on. We'll see some of mathematics later, but at this moment you can easily explain to children this exercise. First of all, they understand very well what does it mean continuous deformation of roads, and then you can explain that you can make in the crossing, you can use only the following rules in your game. You don't need say not simple word for for Russian or maybe even not German children the word Reitermeister, but just to say that you can make 3 rules if you want to change crossings, and then it is exercise for the children for the game when you are in the quarantine. Okay, so very good. If there are no question with this topological exercise, so we can start the next lecture in our theory. So okay, and before just to continue our games, so this is, do you see the screen?
Yes.
Very good. So just to continue a little bit, so today is not very formal, but it will be, I suppose. So just the example of some knots. So you see a knot. Maybe I'll make it bigger. Okay, this is a trefoil. This is a trefoil. We saw that this is the. Actually, there are 2 trefoils, and they are different. We'll see when we'll look at the Jones polynomial. We'll see that Jones polynomial can distinguish. So you see that there is a left-handed trefoil and right-handed trefoil. So what's the difference? And actually, what is the mirror image of a knot? A mirror image is obtained very simple. Of course, you can look at if you have mirror in your room, you can just make this reflection. But if you have a knot diagram, you simply change. You have this branch and this branch, and at every crossing, you change all the crossing of this branch. You change it by undercrossing. So the branch is the same. You localize and look by the glasses, if you want, a microscope. You look only at this small point. By microscope, you are looking at this point, and at every point, you are changing the overcrossing to the undercrossing. So in microscope, you have a point and you have 4 branches, right? And you change overcrossing by undercrossing at every point. This means that you got the mirror image of your knot. Very good. So traditionally they are different, but traditionally it is in the knot tables you have only 1. But again, if you change here to mirror images, you will have another knot. This is called. It's
true for every knot, no? Even the next one.
No, very good question. Very good question. The true, in some sense, means that for every knot you can construct its mirror image. This is true, and this is true that for trefoil, only just at our time, you just fix that the trefoil and its mirror image are different. We'll see, and then the proof without Jones polynomial is very difficult. And I just prepare that we'll wait for it, and we easily, when we apply Jones polynomial to the diagram of trefoil, we simply obtain different values of polynomial, and we will prove that Jones polynomial is invariant. So it will mean that this is different object in knot theory. I'm still trying to reply at your question, and this knot is called figure-8 knot. Figure-8 knot. So you see that in the picture it looks like figure-8, but of course you need this loop to come, because otherwise, if you just make a glue here, you will have a knot. But so this is what is called figure-8 knot, and I wanted to tell this a little bit later. But if the question is, then this will be the next game. The next game for the next lesson, for the next Monday. The game will be to make a system of isotopies that proves that figure-8 knot is equivalent to its mirror image. So it happens sometimes, and you see that example is very close. So you see here, there are two most simple knots, non-trivial knots, if you forget about a knot. These knots are the simplest. This is the only knot with the minimal 3 crossing up to mirror image, and this is only one, the only one knot with 4 crossings. Its minimal number of crossing is 4.
Is it because of parity that, or it's something else?
I don't know. I only see, but maybe I cannot do it by heart. I need to remind. I didn't intend to say it in this lecture, but I see the deformation. So Raphael, I see the deformation. I don't think that this is because of the parity, but I will look at this. But so the next exercise, if I will not formalize it, this will be the next game to show the 4 pictures, which shows that this knot is equivalent to its mirror image, and such knots are called amphichiral knot, the knot which is equivalent to its mirror image. Okay, so this will be our simplest examples, because first of all it is simpler to make pictures of them, and but even to calculate some invariants, it's not always simple. So let us look at these 2. Oh, if you want 3. So this is the beautiful pictures for this. Okay. And now this is what is called the, let us see the links. So sorry, I made a picture, but somewhere I didn't look. Maybe after break I'll fix my pictures. So of course the simplest is what is called the Hopf link. So do you know what is called Hopf link? Natalia? Rafael?
No, not sure.
This is the beautiful name for a very simple thing. I'll try to make a picture. Okay, this is called Hopf link. By German mathematician Heinz Hopf. Yes, so this is the simplest link you can imagine. Of course, maybe if you want the most simplest link, the link of two components is the trivial. But this is a link, and so this is the Hopf link, and it is of the following form. This is Hopf link, okay? So, okay. How to, sorry. So, it's not moving. The screen is not moving, sorry. I don't know how. So hope will follow us forever. Sorry, sorry for that. So this is anyway. You see. Okay. No. Okay. Very good. No. This is the Hopf link. No, sorry. This is the Watershed link. This is Watershed link. So this is also two-component link, but you have crossing in the middle between them. So it is not, if there will be no such crossing here, it will be unlinked. You can, if there will be no crossing, you can simply move the yellow one here. Okay. This is the Watershed link, and maybe this link you know it is in the ancient stuff. It is called the Borromean Rings. You see that if you the basic property of Borromean links is Borromean rings is the following: that if you just look at the couple of them, for example, you look at yellow and blue, you see that they are unlinked. You see, Rafael?
I do.
Yeah, the same way. The same way, any couple of rings, it is unlinked. But anyway, if you consider them as a triple, it will be linked. So this is the very well known in some ancient pictures are depicted, maybe in some armors, even Borromean. So this is very well known things, and we will definitely use of them and see them, and we'll calculate the invariants that we'll see the Jones polynomial, the Alexander polynomial of these links. And so now, do you prepare the scissor and paper? Raphael?
Unfortunately, I don't have scissors at home. I have paper. I will just scratch it. Sorry.
But it is, you can, yes, this is a problem, because I also don't have, because I'm living here, not at home, but so I'm in Moscow in just another apartment, and I could not go to the shop to buy these things. But anyway, we shall ask. Natalia, do you have a scissor and glue? You made a very good job with pictures. Maybe you will do the same good job with scissor. Ножницы.
Yes, scissors, okay.
Ножницы и клей. И картон или бумагу.
Или картон, или бумагу. Ну, да, наверное, я могу все это взять. Ножницу, и бумагу, и клей. Сейчас, и клей, да. Okay, I have scissors and glue and paper. Okay.
Very good, very good. So Raphael, you have something to cut your paper, right?
Yeah, I will manage to.
Yes, and maybe you if I also don't have glue, and even I don't have scotch, so I'm looking at you. So the stuff, what maybe I'll show you before we will look this as a theorem, I will show you the picture. So I'm sorry that I could not, I can simply try to erase my hop. So
you can take a rubber and okay.
Yes, I'm trying to do this.
Okay.
Yes, unfortunately, this rubber is not touching the picture. So our aim is the following stuff. So in R3, to get something maybe not so beautiful, but Natalia, if you can do this in knitting or something like this, you can try to get the following things and to give it to the children to play with that. Okay. So
okay.
So did you understand the idea, which is in this picture? Idea is the following.
We take the boundary as a knot, no?
Yes. So you have a surface. Our aim will be to glue, to make in the real sense, to make a picture which will be embedded. So not excuse me. No, I could not. Okay. To construct a surface.
Can I try glue this surface?
Yes, but we sure. But at first, maybe there is a theorem which is under this thing. Because the key word is that this surface is oriented, because it may be that in the construction which we'll have with paper and scissors, we should be very attentive in order to get the surface oriented. So something that in principle, I think you know what is the Möbius band. Raphael, do you know the Möbius band?
Yes.
But you see that if you look at the Möbius band, what will be the boundary of the Möbius band? You can
just a circle.
Yes, this is the circle, exactly. So in principle, you can construct not orientable circle, not orientable surface, and you have a knot. In particular, this is a trivial knot. But the key property of the surface that we shall discuss will be that this will be the oriented surface. So now formally, of course, we will make this. We have a lot of time to make this construction by as a I forgot the English word. Raphael, can you help me? Bricolage. What is the English word for bricolage?
Bricolage. Build.
Building. Okay, let it be. So our theorem is the following. Let K be a knot in R3. So as usual, I remind you, this is a simple closed curve, even polygon, but you can consider smooth curve. I didn't say it, but maybe I'll say it now, that we were looking at the polygons because it is simpler and to escape the problems of topological knots that may be wild. But you can also escape these problems if you consider smooth knots. But some construction, you should suppose some knowledge of the differentiability, derivé, and so on. So now let, as usual, be a knot, a simple closed curve. You can consider polygon or smooth curve. And this is every knot is a boundary of the orientable surface. So I should underline this. Orientable surface. And this surface is embedded is R3. So there are no self-intersection, nothing. It is just usual embedding of the surface in R3. and it is called a Seifert surface. So the German topologist Seifert was the first one who constructed this surface for every knot. And actually, in the proof that I'll start to do, this will be the detailed prescription how to make this construction Seifert surface. So maybe we'll make a break, 15 minutes break before we'll start this cutting and gluing. Okay?
Okay.
Okay. Я склеила поверхность.
Угу.
Вот такая получилась.
Она у вас ориентирована?
Да, я покрасила две стороны. У меня одна фиолетовая, другая розовая.
Хорошо. Сейчас мы посмотрим, следовали ли вы правилам, которые...
Я старалась. И у меня одна граница, то есть у меня всего одна окружность на границе.
Ну да, нет, ну каждый узел по определению это окружность, только она может быть заузлена или нет. И в этом вся идея.
Я могла склеить так, чтобы получилось много границ. Почему нет? Я прям вижу, как я склею, будет 3 окружности, которые будут не заузлены, если не поворачивать.
Понятно. Ну, не заузленный, может, не так интересно. Надо...
Ну.
Нет,
И значит, если у меня вот это все диском заклеить, это у меня тор получится. А это у меня фэт-граф, риббон-граф такой. Очень интересно.
Вы прямо вперед угадываете, что я хотел сказать, но я и скажу, что род трилистника равен 1. Это в точности означает, что это тор с одной границей.
Угу.
То есть тор, вы про поверхности, как я понимаю, знаете, да?
Ну да, я немножко специалист по толстым графам. По детским рисункам.
Ага. Градендик.
Да.
Ага. Это наш местечковый герой. Я из Монпелье.
Угу.
Ну, тут таких сложностей. И у вас работы на эту тему есть, да?
Ну да, да. Немножко есть. Меньше, чем хотелось бы, но есть.
Здорово. Очень рад. Очень рад. Поэтому очень действительно без лишних комплиментов очень приятно, что вы здесь присутствуете на моих пока неудачных опытах.
Да нет, почему? Очень даже удачно. Видите, как интересно. Я даже склеила поверхность. Мне очень нравится.
Сейчас я возьму что-нибудь попить. Мы будем клеить по науке.
Угу.
Я тебе показываю, какой ты хороший. Никто, правда, не смотрит, видишь? Сейчас посмотрим, смотрит или нет. Видишь, все ушли отдыхать. Вот, никого нет, кроме нас с тобой. Мы с тобой тут сидим и всем показываемся, какие мы классные.
Очень вкусно, кстати.
Это очень вкусно. Вряд ли я могу жевать перед камерой.
Are you with me?
Yes.
Raphael?
Yes, yes.
Okay. So we start with our building of the we start with the diagram. So this is as you remember.
Ой, мне нужно входить в Zoom. Ой, извините.
We start with the node diagram projection. So and projection and take orientation. So take at your this is essential that make any so direction, say better to say let us take orientation, the direction of your node. So now double points in the neighborhood, you have double point. So now to first consider that how to better to say, I'll try to picture that for example at our trefoil, how to construct Seifert circles. Let us take trefoil and let us consider orientation once more. And let it be oriented. Let us take the orientation of our thing. And now consider what is called the Seifert circles. So this will be the Seifert circle. This will be the Seifert circle. This will be the. I'm sorry. Maybe I'm not. It is necessary to continue with orientation. No, I'm very bad in. Okay, let it be like here. Let it be orientation like here. So you are going this way, this direction, and then this direction, and you go here. So look, you go with this direction, and here you follow this one. And then here you have the following circle. Here you have the following circle. And here you have the following circle. Here you have the following circle. And here you have the following small circles. So you can make such circles in your paper. You have the direction at each circle. The idea is that you are following the direction. So you go here, 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 here. And then what is happening? what is the direction? The direction is over there. So for example, here, you go this direction and you don't go to this branch because you will meet the opposite direction, but you go to this direction. Same way, if you follow this one, or maybe I am wrong. Excuse me.
Yes.
Maybe I'm wrong, right? So what should I do? Sorry. This is okay, right?
This absolutely don't understand.
Yeah. Okay. Let us try once more. So let us make I'm very bad in drawing, so so what shall I do?
Let's try on old picture.
Yeah.
In old knot. Yes, in this. Okay, let's try in this picture.
Okay. You have this orientation, right? This orientation and this orientation, right?
Yes.
So now the idea is to follow. If you have here, you are going with the direction of the knot, then you continue, you switch the branch, so you are making smoothing in the points. If you consider it's like a graph, then you make smoothing.
You consider it downstairs and at the projection.
I can turn left or right. Two direction. Okay?
Yes, you should turn to follow the direction.
Okay.
Because if you go this way, you will go in opposite direction.
Wait, sorry. We are considering the projection of the knot now. We are downstairs.
Okay, very good. You get this circle, and then you consider, right, you consider this circle. And the idea is that in this point, you should make a bend. You should glue the bend of the circles that will change the direction. So if you have, I'll try to make a picture. You'll make the following bend in the crossing, so that if you have something like this, you have something like this, and this will be now, this will be the bend. So here you have one circle, you're going by this direction, say, and you switch from, this is the your sheet of paper, and this is also the bend. This is also the bend, and you are switching to another
I must glue this circle on edge. Okay. If we have a graph on plan, in each edge we have a circle. Okay.
Right. Right.
Wait. So it's a twisted ribbon that we glue each time between.
Yeah, ribbon. The good word. Merci, Raphael. Good word. This will be the ribbon. You have the oriented pieces of paper. You have oriented circles. And now the diagram of a knot. Suppose that this is the piece of a diagram of a knot. Now you are filling the circles with a piece of paper. This will be our
basically
surface.
These are discs that we glue one to each other with twisted ribbon.
Yeah, and you glue here and you glue here. And if you see the crossing is now becoming the crossing, which if you look here as a diagram, you have the crossing in the diagram. But if you look here at this drawing as this is a surface, and this ribbon is a gluing surface between them, then you have a surface. The most difficult thing in this building, in this bricolage, is to understand that you are getting the oriented surface. So, and better to understand if you have something to look, to consider that this will be at different levels. You have one disk at one level, another disk at another level. And so you will have the piece of oriented surface glued by several. Here we have only two. Okay, so maybe I'll. Okay.
So out of a graph, we get the surface. This is what's happening.
Right. So suppose that you had this, maybe if I am very bad in drawing real knots, so I'm making this diagram, right? I'm making this diagram. Okay? Suppose that this is the knot diagram. Now I'm making this disk of paper, and it is oriented like this, right? This, I see that this is piece of paper oriented. Now I'm making, so this is, see that this is a diagram, and now I'm making construction. This is at our R2. And now I'm in some sense adding dimension. This is R2. This is at the plane, the knot diagram like this. And now I'm constructing a two-dimensional object in three-dimensional space. At the very beginning, it was one-dimensional object in the plane. The aim is to construct two-dimensional object. Here I'm making a disk. Here I'm making a disk, and where I had a crossing, I'm making a ribbon. So this is the ribbon, and ribbon which is twisted. So this is a ribbon. So I'm making a real ribbon, You see that this is a ribbon, and I'm twisting this ribbon, and this is the effect. That this is an effect of the. If I put now, for example, this this piece of paper over, and this is under, I see that I obtained the oriented surface. I obtained the oriented surface by like this. This is the idea of our work with paper.
Okay.
So right. We are always gluing twisted ribbon.
Right. Exactly. Exactly, Raphael, but precise. Always means in the crossing points of diagram. Always yes. Means here. Here. So we make a disk. I was stupid to not to
let's try, okay.
Correct.
Maybe 3-1, maybe трилистник. We have 2 circle, okay? 2 circle and 3 bundle. Any cross is a bundle. Yes. And we have two circle inside and outside. No.
Let's look. Let us look to the theorem.
It's example for 3-1. We have 2 circle inside and outside. Yes or no?
It depends. Yes. So look. Let us. Excuse me. I explained it so many times that maybe I got it by myself. And just. Where is the theorem? Excuse me. Right. So we start with projection, and the projection is equipped with orientation. So we have neighborhood of double points according to orientation. And the diagram, we make this dissolution of in the disjoint oriented simple curves. Okay, this so yes, if we make this, we have many circles, not just one, but in trefoil it will be many circles. And at each crossing point, we make this gluing. So in the trefoil, it will be 1, 2, 3, 4 discs and 3 ribbons. Okay. So the idea would, we may place these 2 cells at the planes, say at different levels. And all right, so let us remember.
Sorry, maybe example for trefoil.
Yeah.
Okay.
Yes. So yes, okay. So one.
For me.
Yeah. No problem. For me also. Okay. So
can I try? I'm drawing how I understand.
Right.
Okay. Okay. We have just. This is our trefoil, and we have two circles. This is first circle, and this is a second circle. Okay. Inside.
Just a moment. So if we have oriented these, so right, you are exactly right. So we have two.
We have this oriented, and right. We have only two circles. This circle.
Yes.
And this circle.
The big
outside
and the small one. And so what the standard preposition is that excuse me, I just this is essential what I would like to for the better visualization. That is sorry, I'm excuse me please. Sorry. Sorry. Yes. So we now have we can now put these two cells into the planes. In the planes, and they cycle C1, C2, with the first one. A1 is smaller than A2 if C1 contains C2. Okay, so you have the big circle that you were drawing. It will be at the smaller level, and small circle will be over it.
Okay, and we have three bundles. We have three cross, and we have three bundles.
Exactly.
Each bundle connects our two circles. Okay.
Two discs.
Two discs. Yes.
Yes. Each ribbon. We have now three crossings, and we have three ribbons.
Yes, three ribbons, 3 edges.
So you can imagine, Raphael.
Yes, I try to. So wait. So for the trefoil,
if you don't have paper, but you have something when you can put your plates, so you have a big plate, grand plateau, Raphael. And over them, put a small one. Okay. For the trefoil, it's okay. And now, if you have scotch, you make in 3 points you can glue you can glue the small plate
Ваня, можно
in 3 different points.
In 3 different points, but each scotch, each piece of scotch should be twisted.
Twisted, yes.
It should be twisted.
Mm-hmm.
And
so
if you have small plates, so Natalia, you can put a blюдце upper and the more larger тарелка in the bottom, and make these three connections. And you now not forget that each plate is given with its own orientation. For example, the small plate over, it has orientation. And the big plate under, it has opposite orientation.
So, wait, can you just show again why you just 2 discs and not
2 discs?
4?
Yeah, but Natalia made a corrected me very good that if we have trefoil. So in trefoil we have only 2 discs. Sorry, we have discs. You put orientation. I was stupid not to I forgot it. So you have this one. If you follow the orientation, the smoothing, you have a big disc which is oriented, say, right-hand orientation. But, okay, sorry, maybe I'm wrong about opposite. And you have the same orientation, right?
Same orientation, yes. We have same orientation.
Yes,
but
so they have the same orientation, but now.
But we glue together with cross our bundle, and if we have this construction.
Right. Right, but I need myself to remind why it is, Raphael, it is necessary to understand that that you need this twisting at you need twisting at every point. You need twisting, and this this from one hand. When you make a projection, this will give you the crossing point. And on the other hand, it makes you that you'll get an oriented surface. So that's what, when you are doing this for the first time, when I was a student, I made it for the first time and forgot for now. Sorry. So you need to understand this, that you will get the oriented surface. So you mean that you can make the coloring. So you'll try to make to understand where at your surface there will be always two sides. So this is what is necessary to understand. Okay.
Okay.
So if you don't see it right now, so you can, but when you can do this, you just just cut a big point, a big disc with your paper, small point with another, and make these three points, 3 ribbons of scotch. You'll see that finally you get oriented surface. So, for example, at this point, if you have small disc, which is over, and then here you are making you're making this switching, then you can follow the coloring of your surface, and you have the two sides. So okay, so this is the main idea. If I explain so bad, you can try this to do yourself. Okay.
Okay.
Thanks a lot, Natalia. You helped me. I forgot some details, thinking that usually people remember something when they are very young, when they studied, not forgettable when they are old.
I'm very old, maybe.
Yes, but you're right. Okay, I suppose now that we have some ideas. What does it mean? The Seifert surface. Now I'll take this rubber to use pointer. Again, I need to do this, and we'll look at.
But I don't understand why a boundary of our construction is an our knot. Why?
Okay, very good, very good. Then we'll return once more, and yes, this, as far as I remember, what I.
This is my second boundary, big boundary. Okay. This is a circle. This is the second circle, and 3 bundle, and we connect with.
Yes.
Okay.
Better to understand this, Natalia, you should do the following thing. I think better to return what Raphael was saying at the very beginning, and let us consider D of K just a regular projection of a knot. Just consider D of K as a graph.
Yes.
You forget in your knot diagram at the moment, just for a moment, you forget the crossings and overcrossings. You have a graph, and you cut your paper exactly by your knot. Exactly by your knot. Okay? So you have big circle and small circle. So small circle, its boundary is exactly pieces of your knot. And the big circle, also the boundary is the exact pieces of boundary of your knot, right? Only there are, now take a microscope and look at your crossing points. And this changing of ribbons, making twisting in your ribbons, you making these crossings. But in all other points, of your discs, you are exactly following the knot. Okay.
Okay, I understand.
Thanks a lot.
Okay.
Raphael?
Yeah, all good.
So this was very good remark, that maybe not doing an epsilon neighborhood, as I was explaining at the beginning, but just take a regular projection, what I wrote. It is better to understand. Just take a regular projection and cut according to this projection. So you have exactly now all points of your knot are in the boundary of these disks, and you only need to make a delicate work in the crossings. Very
okay.
Good. Very good.
We have one circle and knot, we have one boundary in our surface. Okay.
Right. So, and now what Natalia told before, that if you glue the boundary of the Seifert circle that she produced, you will have the torus for trefoil, and this is exactly the gives us the following definition, that a minimal genus of a surface is the invariant of a knot, and in the case of trefoil, you have that this surface is torus, and this is the first genus, for the smallest genus for the unknot. Of course, this is a trivial remark, that if you have a trivial knot, you can just glue the disk, no problem. And if you put another disk to glue from other side, you will have a sphere. So you see.
But I haven't crossed, and where my boundary, where my bundle. I have one disk and I have two disks for a simple circle, but I haven't crossed and I haven't bundle.
Excuse me. I'm saying the previous your remark that you told during the break, that you constructed Seifert surface, and as we know that every oriented surface is determined by its genus. So every oriented surface, closed oriented surface, is a
Нет,
with G handles, right?
Нет, не получается в конструкцию вписаться у меня. То есть, простите, пожалуйста, я что-то не могу это по-английски сказать.
Да.
Ведь у меня нету пересечения, если я просто нарисую линию, просто окружность нарисую. У меня нет пересечений, поэтому два диска-то я, конечно, вижу, но я не вижу, как их склеить. У меня нет, в этой конструкции нет возможности их склеить, у меня нет пересечений. С одной стороны, а с другой стороны, только что я поняла, что у меня, если есть одна окружность, то будет одна и граница по этой конструкции. А тут у меня две границы, два диска, если я просто беру окружность. А это как-то противоречит тому, что мы раньше говорили.
No,
I'm sorry.
I don't see that there is a. Okay, let us see. Let us see again.
No. In this case, it's very good. But for simple circle, one simple circle, trivial. For trivial, this construction don't work for trivial circle.
For trivial circle?
For this knot.
Very
because we don't have intersection, so we have no gluing.
Right. Very good remark.
Maybe I have only one circle, but I cannot glue.
And you need not to glue. Raphael is right. You have trivial knot. You take the disc and that's all. You
okay. Thank you very much. I understand. Okay.
You don't need to glue anything. And
yes.
You have one disk, and you have the boundary. You can glue. Maybe it's not good.
Okay, I understand. So I'm sorry.
This is no. It's okay. And then you glue another disk, and you get a sphere. And
yes.
So I'm using here by default the fact from the, so in some sense non-trivial fact, that every circle, every surface, oriented surface, non-oriented is classified also, but that oriented surface is a sphere with G handles. Raphael,
yes.
do you know this fact?
Yes.
But this was actually the one of the basic points. So I can tell you that it was a crucial point in topology that the surfaces were classified. And maybe it's one of the most beautiful theorems in topology, that every connected surface, oriented surface, is a disk, is a sphere with G handles. The non-oriented surface is a sphere with H Möbius band. And G,
compact surface.
Yes, yeah, oriented, and even how to say the closed surface, even so without boundary. So this was the crucial fact, and then the topologists thought that they will the same way classify the other manifolds. So they had idea that at first they tried to classify. They couldn't classify the three-dimensional manifolds. They couldn't classify four-dimensional surfaces, four-dimensional manifolds. But there was idea that they can do this. But in I don't remember which year, maybe in 50s, Markov proved that the manifolds, that the problem of classifying even up to homotopy, classifying of manifolds of dimension 4 and bigger, is algorithmically not solvable. So in some sense, classification of surfaces is a very exceptional case. At the moment, people don't know what will happen in dimension 3, but you can see even only recently the people understood what will happen, what happens with the fundamental group 0, the Perelman theorem. So you see that for 3 manifolds, it's also not a simple problem. But starting for dimension 4, even homotopy classification is algorithmically impossible. So the case 2 is the we are very happy that every compact without boundary surface oriented is classified by its number of handles. If you have 2 handles and 3 handles, they are not homotopy, even homotopy equivalent. So the minimal genus of a surface such that the boundary of this surface is our knot is called the genus of a knot. So you see that the genus of a knot, as we understood, is 0, and genus of the trefoil is 1. Okay. This is about surfaces, and this is a picture, the same as Natalia produced. So this is about what I told about genus 1. And now if we considered all our bricolage with paper and scotch, we'll obtain now the first invariant of it will be the invariant of links. First of all, note that the theorems that we proved for knots about, for example, the Reidemeister moves, they are definitely true for the links. So if you have two links diagram, two links are equivalent by isotopy, then their diagrams are equivalent by Reidemeister moves and vice versa. This is the same theorem. And now let us define, of course, maybe you know, but just in this case, this will remind for you and also for me, what is the linking number? Did you hear about linking number, Rafael?
No, I don't think so. Let me read.
Very good. Then I'm very happy that I will tell something new for you. So now let us consider that our link have two components, or it may have many components, but you just fix two of them and look how they are related. So let us consider the components alpha and beta and consider the crossing points. And let them be oriented. So I have the following stuff. This will be -1, right? And if these diagrams are connected like this, then you put +1. So what does it mean? We will use this.
I cannot change. Какая разница между ними? Как их отличить?
Yes. Okay. So you look. You have everything is happening on your table, right? In R2, you have standard orientation, which comes maybe from complex numbers that from 1 to I. This is the orientation, standard orientation of R2.
Okay, I understand.
You consider what is a crossing? That there is two branches. One branch is overcrossing and another branch is undercrossing. In Russian, it is проход и переход. I always have problems with these Russian terms because they are very similar. And in English, it is maybe more evident, more vivid that overcrossing, you see over, not, and this branch here is undercrossing. So maybe in Russian it means переход, and this means проход. Okay. Anyway, and in French, Raphael, it means au-dessus
Au-dessus et au-dessous.
Au-dessus, au-dessous. In French, it is also extremely ambiguous. Anyway, in any point, as we are in our R2, we have standard orientation. We have our knots and our links. Please fix orientation, because changing orientation will change the number, the linking number will change also. So you have your knot, you have your knot diagram, right?
Yes.
And you have the following conventions. You take epsilon at each crossing. By the definition, there are only finite number of crossings. You put 1/2 and number of these crossings. So I made a little bit, it's not principle that you are making 1/2, but just because if you will not do this, you will always obtain the even number. So can you tell me why should I always get even number if I had a crossing? Can you explain why it will always be, if I take away this 1/2, this will be always even number? What we are using here? What theorem? Actually, we already mentioned this theorem in our course. What theorem we are using here? Natalia, you take away the sound.
I don't understand. I think this is the Euler characteristic, but
oh no, this is
no?
too, maybe even, but it's too complicated. It's much more simpler. The argument is much more simpler.
Maybe repeat your question.
Consider two components.
Okay.
Consider, I badly wrote this.
Okay.
Take away
I think this sum is 0.
No. It's always even. Why it is always even? Because of what?
Okay.
Raid master move, something like that, no?
Much more simpler. You are too educated, Raphael.
Well, if there is one cross in, there has to be one cross out.
Right. And this is formalized by what? This is Jordan theorem.
Jordan theorem, yes.
Raphael,
yes.
Jordan theorem, roughly speaking, is what you are saying, that you have the first component. This is say, for simplicity, that this is the disk. How many times you entered the disk, the same times you should go out, because this is by Jordan theorem, it divides your plane in two parts. So if you have your curve. At this point, it is not necessary that it is closed. But anyway, you entered, you made plus or minus here, you quit, you have plus or minus here, you entered plus minus here, you quit plus minus here. By Jordan theorem, you obliged to do this because you need to return to the same point. Actually, Jordan says that you need to return to the same component. But definitely, if your second curve is closed, then you will return into the same component. So Jordan theorem says that your plane is divided into two components, and if you put here plus 1, plus minus 1, plus minus 1, you always have the even number of points.
Okay.
So that's why for simplicity, but you may not do this, but just for simplicity, that you always have.
We can.
You put
we
1
can
over
divide
2.
by 2.
Sorry, you take away the sound, Natalia.
And we can divide by 2.
Right. Yes.
Okay.
So maybe I'm given already the proof, but the theorem is that this integer is correctly defined invariant of two component links. So very simple invariant, but anyway it is invariant. So the proof, and now the proof. Now, Rafael, you are right that in some point Reidemeister moves are entering the game, and especially simple to see that the Reidemeister 2, Reidemeister 1 is of no sense to discuss. So let us say here, no, I'm very bad in drawing again. So anyway, why it is not working? So let us consider Reidemeister 2. So what we have here?
No, we cannot Reidemeister 2 in this case.
No, we have.
In first cross
No,
down and next cross up, I cannot move this line.
Yes, you're right. I made a non-trivial. Yeah, you're right. Absolutely. Absolutely. So I'm accustomed to have non-trivial, and that's my fault. This one, right? This one is okay. So here I have -1, right?
Yes.
Because we are going in the overcrossing, go in the opposite direction. Here we are going in positive direction. And if we now put these two bars, you see that they are equivalent by Reidemeister 2. Here we have 0. Here we have 0. So you mean that Reidemeister 2 does not change the linking number. And the same way, but if you need to be more careful with the third Reidemeister, you see that it always worked. But the question is, why should we not consider the first Reidemeister? Raphael, first.
1 second.
First Reidemeister cross one line, one circle.
Yeah, one branch, exactly. Yes. So, and we are constructing invariant that concerns two components of link. So it is not our subject to consider linking itself and so on. So by the very definition, we are considering two components, alpha and beta. And if you have Reidemeister 1, you see that by the definition it is the same component. Now, as an example of this stuff, we shall construct the linking number of Hopf, Whitehead, and Borromean. So Hopf, you remember. Maybe Borromean you remember also. So maybe I need to show Borromean this is. It's maybe done by the picture, but so let us calculate. Let us calculate the linking number for. Sorry, I'm stupid. Sorry. I don't know why it is not working. Anyway, let us look, it is visible. Let us consider this Whitehead link. You have 1, 2, 3, 4 crossings.
Okay.
And let us calculate. You make at first, but of course, sorry, maybe first one it is necessary to do for Hopf link, the simplest, just to understand that it's still. Let us consider the Hopf link and let us take this orientation and this orientation and let us calculate the linking number of these two circles. So what do we have here?
Sorry.
Yeah.
Sorry. Okay. This one or minus one.
This?
Yes. Yes. Okay.
Overcrossing goes to undercrossing in positive direction.
Okay.
So what do you see? Please mark this. -1 because we are going in the opposite direction, right? And here?
Here it would be +1.
No?
No?
Again, overcrossing, Raphael. This is overcrossing, and this is undercrossing, and it goes from positive in the opposite direction.
So wait, it's -1 and -1.
Right, -1 and -1. So linking number here is equal to -1. You see that it is okay, anyway. It is depend, you see that it depends on the orientation. I change orientation in another circle, right? What do I have? I have +1 here, and here, look. Again, this is overcrossing. Natalia, you see?
Yes.
And this is undercrossing. So again, I'm going in the positive direction. So I have +1 here. So changing orientation changes the sign, but it doesn't change the idea. So it changes the sign. So we have that linking number of the hop here is equal plus or -1. So in some sense, linking number tell us something. And the simplest, you see that this is evident for the children. Natalia, you can ask the children. They see that these two circles like this and unlinked two circles, they are different. And you see that the linking number of this stuff is equal to 0, and linking number of these circles is plus or -1. So linking number serves at least for something. Okay?
Okay.
Questions? Rafael, remarks?
No, it's okay.
It's okay. Very good. Then Watershed Link. We have 10 minutes, so we can discuss Watershed Link. Let us see where I put it. I need this one. Here our So very good. You put +1 if it will be oriented like this, and -1. Very good. So Watershed, where is Watershed? Our Watershed link. Here is Watershed. Let us calculate. So at first we need to orient. I remind you that it works when everything is oriented. Let us put orientation for Watershed like this, and say for simplicity will be like this. So there are 4 points. What do we have? Here you have overcrossing, here you have undercrossing. So when you move from overcrossing to undercrossing, this is positive direction. If complex numbers from 1 to I. So here we put +1, right? Here, what it will be? It will be, we continue this way, and this goes this way, so here this orientation. So here, am I right? Yes. So this is at this point overcrossing. This is undercrossing. So we are moving in this direction. In the positive
It's +1.
Positive. So +1.
Yes.
Very good. Look here. Our move goes somewhere here. This is our direction. And this is our direction. So this is overcrossing. This is undercrossing. It goes this direction, right? This overcrossing, and this is undercrossing. To move, we go this direction, right? So, Raphael, what number should we put?
Wait again, can you say, so wait, the first one down, we are moving from down to up, and the yellow one
from up to down.
We are moving from up to down. Okay. In this case, it's overcrossing again, no?
Overcrossing is here, and to move, we are going in negative direction. I remind that the plane is oriented this way, and we are moving from this to this in negative direction. So we shall put -1.
Wait, from moving from what to what? Sorry.
Moving from yellow to blue.
We are looking on the yellow.
Yes, so, yellow, look, it is in the picture you see definitely that this is
yellow
over.
Is over, yes.
Yes, so it is yellow over here. So we put -1. Now here, this is blue is over.
Yes.
Blue is over. So now this is direction. Goes here. And
we take the direction of what is over.
Yes. Direction of over. And now, contrary to this case, the yellow is under.
Under, yes.
So now we are moving from blue to yellow. But again, we are moving in the opposite direction. Again, we are getting -1. So let us calculate. We should get even number 1 + 1 - 1 - 1. We get that the linking number of Whitehead is 0. So you see that what does the moral of this? That linking number is not so powerful invariant. It calculates in simple cases, it's okay. When you have two linked circles in a simple way, you get a non-trivial number. But if you have a little bit complicated, you have the two circles which are linked in this way, you have that linking number is 0. And this example shows if you admit by intuition that it is non-trivial link, this example shows that linking number is not so powerful invariant. Sorry, I make the light. Okay, and we have still 5 minutes. Can you have questions, Raphael?
Just so wait, just to restart on the two left one.
Yes.
So we have the orientation of the blue one, we have the orientation of the yellow one.
Right.
we are looking what is on the top. So the first one, we look on the blue one.
Yes.
Okay. And the blue one is following the usual orientation.
Yes.
So
Yes.
it will be plus. Then the second one, we are looking at the yellow one, which is up, and it follows also the orientation. So, okay.
Yes. As a game, you can change orientation in one of them, if only in one of them. For example, you can change.
Why? Sorry, just why is the second one we are looking on the opposite direction? Why are we looking from top to down on the right side?
Looking from top to down. Always looking from top. Look here, Raphael.
Yes,
here,
yes.
Here, blue is on the top. We are looking how top goes to under.
Yes.
It goes in the positive direction of the complex plane. Here, the top, and they change. Now yellow is at the top, but the direction is the same. And here we getting -1 and -1. If you can now, as a game, change orientation in one of them, only in one. For example, here, if you change orientation in yellow, you will get here -1, -1, +1, +1. So orientation will change the sign, but here the sum is just the same. So you see now that it is rather weak invariant, that it doesn't look. And just sorry, I'll take maybe a couple of minutes to finish with the linking number. Look at our beautiful Borromean things. You can now consider, because linking number takes into account two components. You can now take two components of Borromean, but by the definition of Borromean, you have any two components, you see that they are trivial. So you have, for example, Jordan here, +1, +1, or sorry, +1, -1, and any, by the construction of Borromean, you have that linking number of any two components here. Alpha, beta is 0. So in the case of the three-component Borromean, linking number also tells us nothing. And this is maybe the last thing I want to say you, that we constructed some invariant, made very simple construction. I think maybe it was the first in the theory, in the knot theory, the first constructed invariant. And sometimes it works, but sometimes doesn't work. So that's all what I want to say, but if you have other questions, I'm listening for you, Raphael, Natalia.
It's okay for me.
Thank you. It's very interesting.
Thank you for following. I'm very happy that you are following me and sometimes correcting me. Okay. See you next week.
Yes. And you, as usual, can you send also the PDF of the lecture?
Sure. PDF without this sound and fun.
Okay. Thank you very much.
Thank you.
Bye-bye.
Bye-bye.
Au revoir.
Au revoir.
Au revoir.